today, let us look at area of a segment. What is a segment of a circle? Let us draw a chord AB on the circle with the center O. Now, the region enclosed between the minor arc and the chord AB, that is the yellow shaded region, is known as segment of this circle. Now let us take another point P and Q on the circumference of this circle. Now, segment APB is called the minor segment. And the segment AQB, which is the region enclosed between the major arc and the chord AB, is called the major segment of the circle. Now, how do we find the area of this segment? Let us join radii OA and OB. Now, the chord AB is subtending an angle theta at the center, or angle AOB is equal to theta. Now, let us try to find the area of segment APB. If we add the area of the triangle AOB, then we will get the area of sector OAPB. Let us rearrange the terms, and we see that the area of segment APB would be equal to the area of the sector OAPB minus the area of triangle AOB. Now we know that the area of a sector is equal to pi r square by 360 degrees times theta degrees, where theta is the angle subtended by the sector at the center. Now, in order to find the area of triangle AOB, let us drop a perpendicular OM on the chord AB. Now, the area of the triangle would be equal to half times base times height, or half times AB times OM. But we do not know the measures of AB and OM. Let us look at the two triangles AMO and BMO. We see that both these triangles have a right angle because OM is a perpendicular on AB. So, angle M would be equal to 90 degrees. OA and OB are the radii of this circle. They are also the hypotenuse of both these triangles. And the side OM is common. We see that by RHS, triangle AMO is congruent to triangle BMO. So, the corresponding sides and angles would also be equal. We can see that AM would be equal to BM. Similarly, triangle MOB would become equal to theta by 2. Now, let us apply trigonometric ratios to the triangle BMO. You could apply this to the triangle AMO as well. So, in triangle BMO, we see that sin theta by 2 is equal to MB by OB. Note that OB is the radius of the circle. Let us cross multiply, and we see that MB would be equal to R times sin theta by 2. Now, let us apply cos theta by 2. It would be equal to OM by OB. Upon cross multiplying, we see that OM would be equal to R times cos theta by 2. So, we know the measures of MB and OM in terms of R and theta. Now, let us go back to the area of the segment APB. We know that AM is equal to BM. So, the length of chord AB would be equal to twice of MB. Simplifying, we get MB times OM. Now, let us substitute their values in terms of R and theta. So, we see that area of segment APB would be equal to pi r square by 360 times theta, which is the area of the sector OAPB, minus r square times sin theta by 2 times cos theta by 2, which is the area of the triangle AOB. What about the area of the segment AQB? We could subtract the area of segment APB from the area of the circle. In other words, we can write area of major segment is equal to area of circle minus area of minor segment. Let us look at a few problems. Find the area of the segment AYB shown in given figure if radius of the circle is 21 cm and angle AOB is equal to 120 degrees. So, area of segment AYB. Let us show the region in yellow color. Now we know that area of segment AYB would be equal to area of sector OAYB minus area of the triangle AOB. Now the area of the sector would be equal to pi r square by 360 times theta. Let us substitute the values and simplify. We see that area of sector is equal to 462 centimeters square. Now the area of triangle AOB. Recall what we did in the previous example. We shall drop a perpendicular OM. And now we shall prove that triangle AMO is congruent to triangle BMO. Let us quickly do that. So by RHS, the two triangles are congruent. This tells us that angle AOM is equal to angle BOM, which is equal to theta by 2 or 60 degrees. Also, AM would be equal to BM since the two triangles are congruent. Now in triangle AMO, we can apply trigonometric ratios and find out the value of AM. It comes out as 21 times square root of 3 divided by 2. Similarly, let us apply cos 60. And we get OM is equal to 21 by 2 centimeters. Now we know that AB is twice of AM. So AB would be equal to 21 times square root of 3 centimeters. Now we can find out the area of triangle AOB. It would be half times base AB times height OM. Let us substitute the values and we get area of triangle as 191 centimeters square. Now we know area of the sector and area of the triangle. So we can easily find out area of segment AYB. It is 271 centimeters square. Let us look at another problem. A chord of a circle of radius 15 centimeters subtends an angle of 60 degrees at the center. Find the areas of the corresponding minor and major segments of the circle. So we have a circle of radius 15 centimeters. Let us draw the radius OA. And this chord subtends an angle of 60 degrees. So let us take another point B. So we know that angle AOB is equal to 60 degrees. Now we have to find the area of the corresponding minor segment first. So let us take another point Y and call it segment AYB. Now recall our previous steps. Let us drop a perpendicular OM on the chord AB. We know that angle AOM would be equal to theta by 2 or 30 degrees. So in triangle AMO, we can apply the trigonometric ratios sin theta by 2 and cos theta by 2. This gives us the values for AM and OM. AM comes out as 15 by 2 centimeters and OM as 15 times square root of 3 divided by 2 centimeters. Recall that AM would be equal to BM since the two triangles were congruent. So AB would be equal to twice of AM or 15 centimeters. Now let us find out the area of segment AYB. It would be equal to area of sector OAYB minus area of the triangle AOB. Now let us quickly apply the formulas for the areas of the sector and triangle and substitute the values. Upon simplifying, we see that the area of segment AYB is 20.44 centimeters square. Now we have to find the area of the corresponding major segment also. So let us take another point Z. We have to find the area of the grey region, the segment AZB. Now this would be equal to area of the circle minus area of the segment AYB. Let us apply the formulae, substitute the values, and area of segment AZB comes out as 686.06 centimeters square. Let us look at another problem. A round table cover has 6 equal designs as shown in given figure. If the radius of the cover is 28 centimeters, find the cost of making the designs at the rate of 35 paise per centimeter square. Now the cost of making the designs would be equal to the rate of the design times the design area. Now we can divide this circle into 6 equal sectors. So the design area would be 6 times area of one segment. We know that the circle subtends an angle of 360 degrees at the center. Since we are dividing the circle into 6 equal parts, the angle subtended by one sector would be 1/6 of 360 degrees or 60 degrees. Now let us look at one sector, and we have to find the area of this segment. We know that radius is 28 centimeters and the angle subtended at the center is equal to 60 degrees. Now we know that area of segment is equal to area of sector minus area of this triangle. This time, let us apply the formulae. So area of sector is pi r square by 360 times theta, and area of triangle is r square times sin theta by 2 times cos theta by 2. You might like to draw up a perpendicular, prove that the two triangles formed are congruent, and then apply the formula for area of triangle as half times base times height. We are taking a shortcut here. Now let us substitute the values. Simplify. And we see that area of one segment is 77.46 centimeters square. So the cost of designs would be the rate 0.35 times 6, because we divided the circle into 6 equal parts, times area of one segment, which is 77.46 centimeters square. So the cost of designs is equal to 162.67 rupees.